Okay, I think it should now be sharing,
Yes.
and I will try to find a spotlight and play. Oh, things are working, right? Very good. Okay, well, good morning, everyone, or afternoon, again, whatever time zone you're in. Um, this is the third in a series of attempts to present a view of suspension mechanics, looking both at the rheology and the ultimately the bulk flow of these materials. And so when we talk about the role of inertia in suspensions, it's much less studied than the case of Stokes flow suspensions. And that's in large part because the fluid mechanics at the local scale is much more difficult. But what these pictures show is that there are some quite interesting phenomena that go on in as the result of inertia in suspensions. And so I'll try to talk about these, but you can see that it goes from dilute conditions at the upper right here, where you have organization, which is quite regular and interesting in a little micro channel. At the lower right is a classic fluid mechanic problem of Taylor-Couette flow, but then with the influence of particles, it becomes somewhat different. And then there's the case of flow in a channel where some very interesting fluid mechanics intersecting with the particles leads to some things that are being displayed here. And I'll save the story for a little bit later. But so I do want to give just a little bit of background, and that is that um, I actually didn't really know how to spell rheology until well into my PhD thesis, and ultimately what I was working on was rheology, um, but I didn't fully understand that because I came from a very fluid mechanical background in terms of what I was trying to understand, and so this effort goes back to my roots of trying to understand the fluid mechanical interaction of the particles, but at the same time then trying to translate that to the behavior of the bulk material, and so that's been the challenge, and we'll see a few things that have been accomplished by some by my group, some by others, but this is just a sampling to give you an idea of the thoughts that are going on in inertial suspensions. Okay, let's see if I can get to the next slide. Well, there we go. So we had this picture that in going from very small particles to large particles, uh, sort of unifying feature for suspensions is that we have rigid particles or rigid or nearly rigid particles in a background continuous liquid, and that goes across scales from the nanometer scale up to the millimeter or scale. After that, you get really into consideration of very granular materials, and so the fluid mechanics is maybe a bit of a different issue. But so being a little bit more quantitative about this, then I want to, sorry, I have to get something out of my way, two things out of my way. Ah, there we go. Okay, so if we look at those length scales here, going from the, tens to hundreds of nanometers up through the micron scale, we have a colloidal dispersion, one where Brownian motion plays a major role. And it's essentially impossible, maybe not impossible, but very rarely would you have conditions where inertia plays a significant role when we're below at the particle scale when you're below a micron. So the Reynolds number here is typically small when we're talking about a Reynolds number based on the particle size. As we cross over into the non-colloidal suspensions where we don't have much Brownian motion and surface effects to become less important um, than the hydrodynamic effects, then we have a different scenario. That here we can have low Reynolds number as long as the viscosity is sufficiently high. Then we can be over here in this Stokes flow or Reynolds number less than one condition where we can throw away convective effects. But once we consider low viscosity fluids, one of the interesting things that's been found is that with water as a suspending fluid, it's quite easy to get inertial effects at the particle scale, even at 10 micron particle scale. Once we get above 100 microns in scale, then it's very common to see inertial effects in the affecting how the particles move. And then we really have to consider the dynamics where we incorporate the entire fluid mechanical description. So we may be able under simple enough conditions where we can get a steady state flow to just consider the steady version of this equation. Very often when we're talking about suspension mechanics, because we're talking about an evolving local structure of the particles, we have to consider the whole Navier-Stokes equations. So this is a challenging problem, but one where numerics has helped a great deal to start to develop some understanding. And I'm going to talk about both numerical approaches to the problem as well as some experiments. So let's just think about it for a moment. I've talked in the last couple of lectures, if you want to call them that, about Stokes flow suspensions, where there is a well-developed theory, if you will, of the dominant interactions, what's happening in terms of structure and so forth. And experiments and simulations can come together with this theory to give us a pretty well-developed understanding of the system. Now, a lot of what's going on in terms of trying to understand these things is moving toward the issue of trying to bring models that allow us to carry things into other applications. But for Stokes flow, I would say that at some level, the dilute systems are boring, and that's because we understand the mathematical description of the flows. We've done this for a long time. That's a very important tool, but it isn't the exciting research question. Where the exciting research questions tend to come in is trying to understand collective phenomena, larger scales. For finite inertia flows, even the single particle problems have certain issues that are interesting because the problem is highly nonlinear with respect to the fluid mechanics. And if you start to ask questions about particle shape, which I will not do, I'll talk about spheres only, then things get to be really interesting. But the analysis, of course, is more difficult. In fact, in many cases, it's not really true that you can do analysis per se. You have to work in a numerical framework, at least mere mortals have to. And there's a much richer dilute system behavior for these systems. Okay, so I want to try to bring out some of these ideas. Again, if you have questions, please interject. I'm glad to stop and try to clarify or just to entertain some interest in a particular area that I may have glossed over. Okay, so inertial flow of neutrally buoyant suspensions, I want to emphasize that I'm going to be talking about this, and I'll bring the point up again just so that you're clear on what we mean. Particles are going to be, for all the cases I think that I'll talk about, the same density as the fluid for the questions that I'm looking at. And that means that we're really looking at the material properties as a function then of how much inertia the particles have. So this goes to the fluid mechanical paradigm, which is to really understand the viscous inertial balance. That's the essential idea of fluid mechanical analysis when we think of the broader Navier-Stokes sort of perspective. And so the phenomena discussed in prior lectures that I was mentioning are explainable, at least, at Reynolds number equal to 0. But the question that we're asking here is what happens when inertia matters, that is, first effects of inertia, and then what happens when it dominates the behavior insofar as we can get to those conditions. So just to remember that when we have suspensions, different concentrations always raise different questions. So when you're dilute, you can ask questions about why do particles take up configurations like this? And this has to do with how the hydrodynamics under inertial conditions lead to them organizing themselves in this way when they started out in a random configuration as they entered into a channel. So that's something that is clearly very different from Stokes flow hydrodynamics, because the behavior there should be that if a particle starts on a streamline under dilute conditions, it stays on that same streamline just by reversibility issues that we talked about in the first lecture. Well, we talked about under concentrated conditions, then you have to worry about whether the particles stay, where they stay in the flow, if they're under concentration conditions that allow them to migrate. But then there are also, of course, questions just of how in the world does the material flow at all when you get to these very concentrated conditions. So for the inertial suspensions, I'm going to be talking about conditions that go from dilute up to modestly concentrated, maybe 35 to 40%. It's a fairly concentrated suspension, but nowhere near jamming. Okay, so we're not going to be talking about conditions at jamming. Okay, so one of the earliest known behaviors of the influence of inertia on particles in fluids or in suspensions, if you will, but under dilute conditions, was that particles would migrate. And so this has led to a significant amount of work that's been done. So I'll go back to the early work on this in just a moment, but showing that in a channel that looks like the one here, this rectangular sort of channel, particles will accumulate along along the long walls. Now there are preferred positions in these long walls. If you perturb these sort of stable positions here, you find that they're only a little bit stable, and it's easy to disturb them to another position. But what Papatsky's group has shown is that you can use this as a way to actually extract out the particles in this microfluidic channel. So you can see that this sort of ideas have been going on now for about the last 20 years. There's been a body of work on doing this type of thing. And so that's a quite remarkable result, that you can completely separate out the particles in this flow. All right, so to be a little bit specific now, I want to set our conditions and the variables we're going to talk about. So when I say the Reynolds number without qualification, I generally mean this Reynolds number, which is that it's based on the shear rate of the flow, the particle size, the mutual density of particles in fluid is rho, and the viscosity is then mu. So you should note here, if you're thinking about bulk Reynolds number, typically then, because this is defined in terms of the shear rate times a particle size squared, that a bulk Reynolds number scales as the bulk length scale divided by the particle size squared. And so for Reynolds numbers, which are getting up into the upper range here, it's very easy for these Reynolds numbers to get quite large, and questions then of the stability of the flow to different flow transitions becomes a significant issue. So that's a much bigger Reynolds number than the Reynolds number on the particle scale. So we're primarily going to talk at first about the Reynolds number on the particle scale and how that affects both the fluid mechanics at the particle scale as well as the interactions, and then working toward understanding the bulk behavior. So again,
Sorry, is
yes,
it possible to ask a question regarding this?
sure, please.
So how is it possible to know whether bulks will form or whether the particles will remain side by side on their own?
Whether what will form?
I mean,
W.
because if you're talking about the Reynolds number of bulks, it sounds to me that the particles will kind of gather together and stay.
Okay. Let me be clearer on this then. The bulk length scale would be, for example, the length scale of this channel. I want to be clear about that then. I don't think that was clear. That's not the length scale of a particle structure. It's the length scale of
Okay,
the
sorry,
the
thank you.
flow. Yeah. No, thank you for the clarification, because that may have been confusing to others as well. Right. Okay, so then the volume fraction in the usual way that we've been talking about is based on the volume of a single particle times the number density. I'll be talking about spherical particle systems. And the Peclet number almost invariably will be tending toward infinity if I have a finite Reynolds number. It's almost impossible to get significant Brownian motion and have a significant amount of inertia at the same time, bulk fluid mechanical inertia. Okay, so you can actually do a ratio of the mass transfer properties versus the diffusion properties, the momentum diffusion properties, and see that it's really not likely that that will happen. Okay, so for just a moment here, let me emphasize that in much of work where people worry about the inertia of particles, they talk about the Stokes number. And the Stokes number can, roughly speaking, be thought of as the density of the particles divided by the density of the fluid times a Reynolds number, which for the case, I'm going to show a little movie here, of particles settling would be the Reynolds number of that settling motion. So the velocity and the particle size would enter into that. So that's important because it tells you something about the stopping time of the particles. But for the case that we're considering, which is neutrally buoyant, then rho p over rho f is 1, and for all intents and purposes, up to a constant multiple. If I chose to have another way of defining the Stokes number, then the Reynolds number is sufficient. So that's enough to describe the system, the Reynolds number and the volume fraction. I'm gonna let a siren go by here. All right. So a few examples here. Just this is you see this characteristic sort of fun font, if you will. This is comes from work of Hamid Haddadi, and he was very fond of these sort of playful fonts. And so he was also very fond of making nice movies. So I'm going to make use of a couple of his movies here. All right, so the tubular pinch or particle migration due to inertia effect was discovered. I think there's actually an earlier paper from 1961 by Segre and Silberberg, and then has been studied through the years by a number of groups. But what's seen here is particles flowing in a tube or in a rectangular tube, so circular or rectangular tube. And what we see is after a while, they started out uniformly distributed, and then there's none in the middle of these two flows under these conditions. And so this is what's known as the tubular pinch effect, because you start with a uniform concentration and then the particles pinch to a particular radius, right? And because these are at significant concentration, that single radius, which would be seen for dilute enough conditions, becomes distributed into a dispersed layer because of particle interactions creating a level of diffusion, hydrodynamic diffusion. All right, at the bottom, taking a relatively classic flow of flow past a bluff body into a microfluidic device, what we see here is particles at about 8% by volume, the dark, are going past this post, and there is a region where there are no particles whatsoever behind the post. And so understanding why this happens actually involves a number of questions that are not fully resolved yet. But what it shows us is that we really cannot predict these sort of phenomena based on bulk equations of motion. There is no present way that if we take a bulk model of this flow that we are able to describe this. At least that's my opinion. And if it was out there, I would be very excited to see a model that was able to predict this reliably. Some of the phenomena that occur because of migration or becoming trapped in zones are actually quite useful. So the influence of inertia, I showed this separation that came from the group of Ian Papatsky at University of Illinois in Chicago. But here from Dino De Carlo's group at UCLA, this is an inertial flow in microchannels, which are carefully tailored in ways that give them vortices such that they're able to trap particles in these vortices. And this, when you consider the fact that you have both deformability and you have also inertial effects causing migration, then you have some knobs you can tune for doing separation phenomena. This has been used to some advantage in doing cancer cell separation when you have just a few cancer cells among 10 to the sixth, being able to get them to separate out and become more concentrated can be quite valuable. So in fact, I would say that there's quite a lot of work that's been used where there's efforts to use inertial migration in small channels as a way to separate particles from the flow. Okay, so it's not all just fundamental issues. It really does matter. Okay, so I'm going to just briefly, very briefly, without going into any details, describe the solution method that we use to simulate these flows. So if I tried to describe it to you, you'd be bored, you wouldn't learn it. So I'm just going to give you the words here and the places to go to look for more about this. Well, we use the lattice-Boltzmann method for suspensions to describe the fluid phase of the of the suspension. And so the Lattice-Boltzmann method in this context is simply a way to solve the Navier-Stokes equations. It's just one method. It's a slightly compressible method. We work at low Mach numbers for those who are interested in that. And this was laid out first by Tony Ladd back in the early 90s, and then by Cyrus Aden and his group. The method that eventually has, I think, taken hold the most and perhaps is worthwhile to look at was developed by Aden's group. So the results that we're going to use, though, actually are from these two, primarily from these two papers. And in fact, I'll mostly describe stuff from Hamid Haddadi's work in the simulations. Okay? There's another paper that I haven't mentioned here. But so we have Newtonian dynamics for the solid phase. So we solve just Newton's equations where we have the translational problem is associated with the force, and then the rotational this is the rotational equation is based on understanding the torques and how that affects the rotation of the particles. And here, this is the moment of inertia, m is the mass. So we do have to correct for closely interacting particles. That is, even for these systems, we have to be careful. If the particles are going to be extremely close together, then we sometimes have to put in a lubrication patch for these systems. So I want to say a few things about, oh, sorry, I missed 942 again. Sorry. The Hitchhiker's Guide is not truly the Hitchhiker's Guide, sorry. But at any rate, so I'm going to talk about simulations under for a couple of different scenarios. One is looking at just trying to understand single particle, two particle dynamics, and then the properties of modestly concentrated suspensions in just simple shear flow. So just the simplest of flows. And then I want to look at some simulations where, using this problem, which I've described as a motivation, we ask the question about flow over obstacles, just to show some interesting things that happen there. Well, I think they're interesting. All right, so recalling what we talked about in lecture 1, I believe, that for Stokes flow, then we have this separation of the streamlines around a single sphere. So this is single sphere, right? So single sphere, this is not really a suspension problem, just the fluid structure interaction of one particle with a Stokes flow. And so we have these closed streamline regions, and that's a region which extends off to infinity for the Stokes flow. And then we have the open streamline regions here. So you can separate this flow of a particle that's rotating with the bulk vorticity and resisting the deformation part of the flow, gives us this open and closed streamline structure. Okay, so we need to see now what happens when we take the Reynolds number to be greater than 0. And so here's a movie that I hope will play at a reasonable rate for you, and then I will show some pictures at the same time. Okay, so start the movie. All right, so this is just to look at the streamlines around a single sphere in simple shear flow. So here are tracers that move on these open streamlines. So these are simply tracers, they're not other particles. Then there are reversing streamlines. So let me bring up pictures of those. Then there are streamlines which actually spiral around the particle and then away. Okay, so those look, let's see if I can get that to come up. If there are, if you consider a tracer in an off plane, off the shear plane position, it will spiral toward the plane of shear of the particle and then away. So let me just say what's going on here. So again, if I have a streamline that's sufficiently above the 0 plane of where y is equal to 0, y being the gradient direction, then I'll just pass over this particle. However, if I'm close enough to the axis, oddly enough, the flow will come toward this particle and then turn around and go the other way, right? It will reverse. Then if I consider a position which was basically in the closed streamline region for the Stokes flow, it turns out that that region will lead to a slow spiraling outward, and eventually, you can see it here, it departs from the position of the particle. And because of this spiraling out, then I have to have a return flow from down the vorticity axis, and that's this green region, which is the flow which is coming in down the vorticity axis, spiraling until it spirals away from the particle. So rather remarkable set of structures at this scale. And as I point out, there are similar results for drops. And so this, what I say for suspensions, applies for emulsions as well at some level. Okay, so this is work from Kaushik Sarkar at George Washington University. All right, see if I can pass on. So now the question is, all right, so a tracer can be thought of as you can then say, well, if I would took a particle at the same position, what would happen? And so instead of taking one particle, we want to then ask the question of what happens with a second particle in relation to this, that is, what's the pair trajectory, which we found to be rather important in thinking about Stokes flow. And then I want to ask what happens when you consider two particles, any two particles. We take the statistical description of what happens for a pair of particles in the suspension. So we want this red and the blue particle here to be replaced then by any pair of particles. And we ask, as a function of separation and volume fraction and Reynolds number, what's the behavior? All right. So here we can see the streamlines which actually pass one another. So these are the passing streamlines. Here are reversing streamlines. And then we have the spiraling trajectories. These aren't streamlines, these are trajectories, to be careful with my words. And we actually see then also this spiraling down the axis toward one another and then out away from each other. They'll eventually depart. And so everything that we saw in terms of the streamline structure is carried over into the topology of the pair trajectories. So if we look at those pair trajectories, then we have the open trajectories are the black ones. We see then the reversing are the blue, and then the spiraling are the red. As we increase the Reynolds number, this is a very small Reynolds number, one would think, at the particle scale, and yet it is affecting the behavior over a significant part of the flow in a meaningful way. At a Reynolds number of 0.6, these closed streamlines come much closer to the single particle. So remember, this is taken in the frame of reference of the particle at the center. Then I'm asking, what is the relative motion of another? And of course, if this is in a simple shear flow, then this is a symmetric interaction. And so you have to think about this in terms of the relative motion of the pair. If we look at the bottom, then the off-plane trajectories are compressed as the Reynolds number goes up to closer to the particle, and the general structure, however, seems to remain about the same. Okay, so you could ask, well, yeah, Ashif, yes, question?
Yeah, I'm just trying to understand the previous one of the previous slides where you talked about the tracer, like you are
Mm-hmm.
basically seeing how the tracer behaves, and in that slide, what I could gather from, like, I may be wrong, like what I understood is the tracers is basically approaching the particle. It's like is like kind of attractive potential or something like that. I don't know what exactly how to understand that, and then it gets reflected back,
So
or
there's, you could,
does it cross each other?
so So these trajectories cannot possibly cross each other because these are fluid mechanical tracers. This is
Okay.
just, if I had an experiment, it would be the same as if I put in some tiny, tiny little bubbles that would stay put if I didn't, they're so small they can't rise or settle. But then I shear the system and they trace what the fluid does around the particle. So these, let me just go back. If I had a tracer here, it would follow on whatever streamline it's sitting on, and it's the exact equivalent of that carried over here, where now I ask, what do these tracers do? And so I have a line of them now far enough away. Then they pass over the particle. Here, they actually come in close and then turn around. And so the ones that come in close are coming in from close to the y-axis, close to y equal to 0, in the shear plane, you see that they come in and then they reverse, and that extends out into the vorticity direction as well. So the trajectory space is, the streamline space is quite complicated when you have finite inertia around a particle or a droplet, as Kaushik Sarkar has shown.
Right,
And
but
that,
what I was thinking is if you increase the Reynolds number
yeah,
gradually, you will you see some kind of crossing at some point?
not, no, not in this scenario, no, because
Okay.
this is a steady state fluid mechanics around one particle.
Mhm.
So it's a steady state fluid mechanics, so no two streamlines can cross. And this is just a tracing of streamlines.
Okay. Okay. Thank you.
Yeah, thanks for the question. So the things now are going to get complicated in a way that addresses what happens really in the suspension under these conditions. So now think of taking any particle and asking what any other particle does in its trajectory moving toward it. Okay. And so this is the statistical physics question that one has to answer to understand the average behavior at the pair level. So here's the particle one, my reference particle, and any of these lines out here are the positions at time, starting at time zero, say over here on this area for the red ones. And as I shear the system, this is the paths of all the sampled particles, or some large number of sampled particles. And what we see is that there are these regions here, which are the reversing trajectories. These are reversing trajectories. These blue are spiraling trajectories, and the red are the passing trajectories. But that trajectory then has an average, which we have to do some averaging of this data to get. And then clearly there's quite a lot of fluctuations. Okay, so this is at 25% volume fraction and a Reynolds number of 0.6 on the particle scale. Right. So there's a lot going on, and this is the evidence of the large number of interactions that the particles are feeling with the surrounding particles. Okay, so it's much like if I ask molecular dynamics of a molecular system, then I have to sort out the average from the fluctuations. We have to do the same thing here. And so one of the more remarkable things is that the spiraling trajectories survive even under these conditions. Even here, it's at 15% volume fraction, and you see the average trajectory of a particle that starts at this position has this form where it spirals in toward this reference particle and then departs. And as we go to a higher Reynolds number, that was 0.6. As we go to a higher Reynolds number, which is actually quite large for what we do, this is a Reynolds number of 2, then that's compressed, but there's still this finite zone of the spiraling trajectory. And that continues right up to 25%, and that's as far as we've actually analyzed this question. But I want to emphasize that that is very puzzling and surprising, right? That this happens, that the behavior retains this, but it tells you that the continuum motions, which are induced by the fact that a particle exists at a position, are important and carry over to a significant distance. Sorry, I have to plug in my computer here. So, okay, here we go. Okay, so I hope that the what's being shown there makes sense. Is there another question or no? Okay. All right, so those are the basically the spiraling regions. All right, so when we talked about concentrated suspensions in Stokes flow, one of the key issues in terms of understanding the rheology was to understand the pair distribution function, or the likelihood of finding a particle at a given position. And so just considering the contact positions in the plane of shear, so this is considering particles relative to this shear flow, where 0 is the position where they would be aligned along the flow, and then pi is where the second particle is. It's the symmetric position where it's all the way to the other side of the particle. What we see is that over the entire region where we have the extensional flow, there's this very depleted zone in terms of the concentration of the relative likelihood of finding particles. And as the Reynolds number increases, we get a much, much higher correlation at contact. So it's following what's been seen in Stokes flow, but here you see the influence of the Reynolds number causing this to become larger and larger. And when we see the contact correlation, we're actually talking about the value in the nearest bin where this was sampled at 1/1000th of a radius, right? All right, so then if we go to higher concentrations, we're seeing behavior that starts to look actually more like the Stokes flow conditions. It's not quite as extreme in terms of the depletion in the extensional flow zone as it is when we are at the low concentrations. Okay. So there's a lot of similarities, but then we see the influence of inertia playing a role in what the correlation actually is. So the goal of having that sort of structure is to rationalize the just a moment, I'll answer those questions, but one of the goals is to rationalize the suspension properties. And so in order to do that, we have to consider different contributions to the stress. And I'm only going to talk just for a moment here about the stress-lit contribution because it's something we talked about last time. So let me answer the questions then. So.
Oh, it's just a quick question about the previous plots, the previous slide. Have you checked the same, but in the other plane, in the other direction? Like in the plane in the...
Yes, I mean, so we have the entire pair distribution function over all space, and I would have to say yes, we've done that, and we have the results, but do I remember what they look like exactly? Yeah.
Because I would guess that those spiraling trajectories would appear as a signature in those correlation functions. No, I don't know, maybe. I mean, they're not really touching in those trajectories, but
yeah, there may be some hint of them because there is then a velocity toward contact in that direction, but it's a quite weak and slow flow that's mostly a motion tangentially. So
sure.
Good question, but I don't say that I've seen anything terribly significant.
Okay, thank you.
All right, so the first thing we had to do really in all of this was to compare against some of our own work and others looking at single particle influence of inertia on the rheology. So remember, the stresslet is this symmetric moment of the tractions on the surface of a particle, and so it can be calculated at a single particle level, both numerically and then by perturbation approaches for numerics. For theory. So what one finds from that is that remarkably, there is a contribution to the first normal stress difference and the second normal stress difference that scales with the volume fraction of the particle. So the volume fraction should be scaled out of this as well. And so we see that there's this significant increase with the Reynolds number of this behavior. So while the system is very dilute, what it's saying is that the influence of the particles on the rheology is immediately non-Newtonian. And so that's something that's different from Stokes flow. And in particular, then we just focused here on the normal stresses. So I'll say then a little bit more about the viscosity on the next slide. Will I? Maybe I won't. But so let me just point out that if I had a Stokes flow suspension, so this is results of accelerated Stokesan dynamics from Mina Siru with John Brady. And so what she did was consider these conditions up to 35% volume fraction. So what we said was, well, what's the influence of inertia on this? And we see that there's this quite strong effect even at small Reynolds numbers on this. And that's because this would be essentially a Newtonian material because you have to have pair interactions to get non-Newtonian behavior in Stokes flow. And so here, the single body gives us the result, and so it's a much larger result. And then all of these increase with volume fraction and increase with the Reynolds number. Okay, so that's the first normal stress difference. The second normal stress difference, which for Stokes flow suspensions tends to be negative. So here, you see this is a negative N1, and so minus N1 gives us these positive values. Here, N2 would be negative for Stokes flow suspensions, and so we see the Stokes flow behavior is all negative. What we see, though, at low values of the volume fraction is that for significant Reynolds number, we get positive values. And so this is dominated by inertia over the influence of the interactions, let's say. But eventually, at high enough concentrations, then we get behavior that's dominated by the interactions. And so it's like the Stokes flow suspension. So there's sort of an idea that comes out here is that once the concentration becomes large enough, rheologically, the material tends toward the Stokes flow conditions, even if at the particle scale it has significant inertia. And that's I say that it isn't exactly a proven result, but that's been my impression of the behavior over the years. And so that's those two regions. And the same holds for the particle pressure, which I won't say anything about here. But you see that in general, the influence of inertia is to cause a thickening of the material, a greater dissipation due to higher Reynolds number. And so roughly speaking, what that means is that the particles are getting very close together with more velocity than one would otherwise expect. And perhaps they're also developing structures which are larger and cause larger disturbances, going back to a question that came up earlier about structures. So we don't exactly understand this. Okay, so that was looking at properties of the system. Now I want to ask questions about the fluid mechanics of the system and under conditions where we can do simulations. So wake forming flows of this sort have been studied for forever, basically, since it was possible to study these kind of flows. And people looked at these kind of wakes off of bridges behind the pillars that held up bridges long before they were doing experiments. So the idea of this is central to fluid mechanics, is the concept of a wake. And so we ask, well, what happens if tracers are replaced with finite sized particles? And so I've already shown this movie, so the picture is sort of already in your mind, is that we have then a depletion region in the recirculating wake area. Now, I do want to point out that this is a flow where it's in a microfluidic channel where the height of the post that you're seeing, the square post, is actually smaller than its dimension. Its dimension toward us out of the page is about 80 microns. That's between two plates, and it's 200 microns in the square sides. The particles in this case are a few microns in diameter, about 3 to 5 microns in diameter. And so what we see is that even for particles that are of this scale, they are behaving in a way where they very definitely don't behave like tracers, right? So there's a region here which is depleted. Now, it turns out, because of what I just said, that because this is in a microchannel, the three-dimensional flow plays a role. The three-dimensional role in the wake plays a role that I'm not going to talk about here. But what we wanted to do is to see how much of this behavior we could understand based on just a two-dimensional representation, not truly a 2D representation, but an infinitely extended cylinder done by periodic replication in the third dimension. Okay, so that's what these simulations are showing. And so you're living inside of the simulation there for a moment. Okay. So let's again take the perspective of backing up a little bit. So we've seen that we can simulate it, and there's some interesting things that one can get at the bulk scale. But let's just back up and look at what happens to the system. So if I take a single particle and it's released, then it released upstream, it never can enter the wake, right? So it's held far enough away from the surface here that there's no way that it can cross the separatrix to get into the recirculating wake. And by contrast, if a particle is released in the wake, it will migrate, right? So it doesn't do what it would do in a Stokes flow and just stay in the same position. You wouldn't have these wakes in the first place for a Stokes flow, but it actually migrates outward and it reaches a limit cycle. And in fact, it can reach that limit cycle from a certain limited set of trajectories outside as well. Right. So remember, this particle is the same density as the fluid. So what's happening is due to inertial effects interacting with the particle interacting with the fluid. And so the inertial migration to this limit cycle is faster. So there's more separation, there's more migration per cycle around the wake as we increase the size of the particle. Right? And so the Reynolds number here on the particle scale is, I think, of order, let's see, this is of order about 40, I think, but I'd have to be careful. Okay. Okay, so now here's a fun question. So we could take bets or we could have a poll, but we don't have time. So if you put a number of particles into the wake region, so this is the recirculating wake region, 2 lobes, we can ask which one of these 5 particles will leave first, right? So you can put the bet down, write it down beside you, write it down, tell me your bet. Well, you don't have to tell me, but you have to tell yourself. And then let's see what happens. Okay, so here they go. First thing you notice is that because of interactions, these aren't perfectly smooth lines. And then you see one cross the separatrix to the other side. It got pushed over there. So hydrodynamic interactions pushed one out. These are the only particles in this flow. And then I know the answer, so I have to just be quiet. And here we go. Here we go. It's going to happen soon. Any bets? Did you? Oh, there it goes. And so what we see is that number 1 was migrating outward, inward. Lots of things were happening, but then because of an interaction, it got pushed outward and it crossed the separatrix and it leaves. So this is one of the things that has to be accounted for in any thought process of modeling these systems, is that the interactions lead to the ability to cross in and out of this region. And we spent a lot of time worrying about that, but I just wanted to raise the issue, not try to delve into it too much here today. Okay, so I want to move on to a different flow, and that is the classic case of the Taylor-Couette flow, but consider it for suspensions. So for the pure fluids, there's a well-known work from Andrich back in the 1980s that showed that there are a wide range of different flow structures that are formed, and this is just a small sampling of the entire menagerie of conditions, of flow conditions one can get, depending on whether you have counter-rotating or co-rotating cylinders. So when I talk about that, what I'm talking about is this flow, that is just a Couette flow, but this, I can have the inner cylinder and the outer cylinder rotating either in the same direction or opposite directions. Or in the case that I'm going to talk about today, I'm going to have only the inner cylinder rotating and the outer cylinder fixed, which means that I'm on the line that goes just straight up and down here, which will be that I only have the inner cylinder Reynolds number being finite, and the outer cylinder Reynolds number, that is based on the motion of the outer cylinder, is 0. So if you're at low enough Reynolds numbers in general, you have just this circular Couette flow. And then there are a wide range of other conditions that one can get. You can get Taylor vortex flow, these beautiful counter-rotating vortices coming in pairs. You can get wavy Taylor vortices, and these are just showing the particular abbreviations. I couldn't think of the word. The particular abbreviations we'll use. And then we have a region here in red, which is a spiral vortex flow. And I want to emphasize this funny little region here, because there is no spiral vortex flow on the line where we're going to do experiments if I'm considering a pure fluid. For a pure fluid, this state doesn't exist along this axis. And what I'll show is that it does occur for suspensions for reasons that are presently unknown. So the first thing is we've been talking about migrations. And so what one can see is that if you have a suspension, dilute suspension, you can actually see that the particles move in this Taylor-Couette flow. After some time, they go from well-distributed on to particular positions. So they form limit cycles in this flow due to the migration that was just described for the flow past a cylinder. Something similar is happening here. And so if we consider what happens as a range of over a range of Reynolds numbers, this is all for dilute conditions. So what one's seeing here is an overlay of many images. And so what we see is that once I pass into the Taylor vortex flow region, so I'm above the circular Couette flow, so I've transitioned, then I see the residue of that flow, and I see a changed structure as the internal vortex becomes stronger. And so that vortex is the strength of it, you can see in terms of the radial velocity relative to the characteristic velocity of the inner cylinder. It's small, but it gets larger as we increase this Reynolds number. And once we get to a high enough Reynolds number, we have these very clear positions for the particles. But then we go into the wavy vortex flow, and the particles are well distributed, right? So there's something interesting that happens there, that there's not the ability to organize the particles in this way once we get into the wavy vortex flow, even though fluid mechanically, this is still a highly organized flow. So the fact that we have in the wavy vortex flow the distribution allows us experimentally to find a way to study the system without much migration. So particles like to migrate in these flows, but we'd like to have them well distributed over long periods of time. And so what we do is we start in the wavy vortex flow and ramp down in Reynolds number slowly with time. So the Reynolds number is shown as a function of time. And then we take images and then just take the images down this central strip here. And what you're seeing is with lighting from a particular angle with a material that reflects the light. It's little flat plates that are put into the flow at very low concentrations. They give us the ability to see the structure of the flow. And so we take these pixels along this line with the decreasing Reynolds number, and we get this spatiotemporal diagram for the flow. So this is time, and this is the behavior along this axis up along the annulus. And so that can be replaced by the Reynolds number, since we know the Reynolds number is decreasing as a function of time. So this is the high Reynolds number, this is the lower Reynolds number, and you see it going from a wavy vortex flow to a Taylor vortex flow to a circular Couette flow. That's what the meaning of this picture. And so if we look even at 10% particles, so we have 10% of neutrally buoyant particles that are the most carefully neutrally buoyant particles that have ever been made in my lab, that we spent, well, Madhu Maji, who did this work, spent enormous amounts of time making sure the particles didn't rise or settle. So for pure fluid, here's the wavy vortex, Taylor vortex, circular Couette that I just talked about. And this has transitions at a Reynolds number based on the pure fluid viscosity in this case, of course, at 151 and 120. So 120 is very close to what's seen in all work with this particular ratio of the sizes of the inner to the outer cylinder. For the suspension, at 10% particles, and the particles being 1/30th of the gap size. So the delta dp is the gap size, that is the annular width divided by 30. So it would take 30 particles to cross the width. We see that this first transition from the wavy vortex flow occurs at a significantly different Reynolds number. Now this Reynolds number is based on the particle volume fraction, so we've already taken out the influence of the dissipation, and so this is just an effective fluid description for the Reynolds number. The transition to the transition to the Couette flow is at 107. So that means if I was increasing the Reynolds number, this is the first place that it would go unstable, is at 107. And in between here is a state that doesn't exist for the pure fluid, and that's the spiral vortex flow. So somehow the structure, which is seen when I have counter-rotating vortice cylinders, is actually occurring for a single cylinder rotating in the case of a suspension. So the dynamical system has been shifted, is the best way that I can think about it. It hasn't been fully rationalized yet. So there are some movies, but I'm going to show some other things here for the sake of time. So if I then consider higher concentrations, 30% solids, what we actually see is this wavy spiral vortex flow then giving way directly to the circular wet flow, which means that there are no symmetric states seen above the transition. So only no axisymmetric states. So the Taylor vortex flow is a vortex which is symmetric around the entire axis, around the entire circle around, if you're considering the flow. That does not occur. There are no states which we find that are axisymmetric at this concentration above the transition away from the circular wet flow. So the dynamical system is shifted even farther. And this is, I would say at the present time, not understood at all. And issues of this sort are being considered across a number of groups now. And you can see just there's 3 papers in the last year that are in this half of 2024 that are addressing trying to use this flow to understand multi-phase flows in different ways. So some are quite directly related. And then these 2 older papers are showing just 2 different groups who have contributed quite a lot of understanding to this system as well. So this is from Mahbub Alam and Christian Pulma. Okay, so let's see how much time I have here. Okay, in the last, say, 5 minutes at most, I want to just say a little bit about another flow, which is, from an engineering perspective, an important flow. If you think about flow in channels or pipes, it's a central one in trying to make use of suspensions in different ways, either transporting them, flowing them into molds, if you're doing something like ceramics and so forth. So here, let's consider a bifurcating channel flow. That is a flow which is entering, as this arrow is showing, in this way, and then it splits at this T junction, right? As you go up in Reynolds number, you start to see this separation zone and then this behavior. But this is for a 2-dimensional channel. That is, if this channel was extended infinitely far in the page, this is the flow that one would see. And so we've studied the asymmetric channel where you flow in this direction and then out this way and out this way. So this was Sojwal and Manurkar's work. But what I'm going to talk about today is the symmetric channel where the flow comes up and then divides symmetrically out in both directions. And so that's all I'm going to talk about. So this is single phase fluid mechanics solved by COMSOL, right? Easy to do. And so then we go to the 3-dimensional case. And in the 3-dimensional case, equally easy to solve by COMSOL, but remarkable flow structures occur, right? So now these streamlines are rather complicated. And in particular, when you get to about a Reynolds number of 100, you start to see spiraling, and it becomes rather obvious here. You see that there's a streamline coming straight down. I only show the ones going to the right for simplicity here, clarity, I hope. And you see that it spirals out as it goes outward, right? And there's a very intense spiraling region. In fact, Howard Stone's group has shown that you can capture bubbles in these regions. So there's some interesting work that actually preceded ours. We actually found this phenomenon, and then we found the paper that Howard Stone had written about it. So that may be an experience that others will experience in their careers as well, as finding a phenomenon and then finding that Howard Stone had already observed it. Okay, so let's see what happens when we put particles into this flow, because this is a rather complicated flow. And so what we did is we took 2 high-speed cameras and we looked at the bottom. We're looking into the flow. Let me go backwards just to say. So we're going to have one. I have to go backwards, and it's not allowing me to do that. There we go. So I'm going to have a camera effectively that's looking down the axis where it says Reynolds 460. There's a camera right here, and then there's a camera above looking down into the page from the position of my spotlight here. Okay, so there's one here looking this direction, and then there's one here looking into the page. And so what we see is then particles, as they're moving in, this is at 10% particles, obey the same form of motion. Another feature you see is that there's a very strong recirculating zone here. And particles actually will, if you watch them over long periods and track them in both directions, you can see that they actually will move toward the walls and then leave the recirculating zone, and then others get pushed in. But you can see this very interesting behavior. So we were shocked by this behavior when we first saw it, because we thought it was particles that were bouncing at first, and then we saw that they weren't touching before they bounced. And then we found this other paper by Howard Stone. Right? But so you can see the behavior is due to the fact that the particles are, well, I'm not going to try and explain the development of this vorticity, but what happens is the flow is coming toward the wall. It has to then split, and it splits in two directions, and that induces then a spiraling motion when the Reynolds number becomes large enough. So what we've done then is, because we have these tracer particles with others that are nearly index matched, we can track the tracers. And so what we see here for 10% is that certain of these streamlines have very, very similar features, and we can track the particles. This red line is from the calculated fluid mechanics. As closely as we can, we match the trajectory at the beginning, and we see that there's a behavior that's very similar. But the particle, because it gets very close to the wall, essentially gets stuck by lubrication interactions, and so it's not able to adhere to that streamline. But if it's in a position that's a little bit farther away, then we see that it behaves roughly speaking like the fluid mechanical motion, but it shows that it's very hard to find exactly the right position to track. And so this is just showing it from both directions in each of these cases. Right? All right, so when we go to a little bit higher volume fraction, so here what's done is that there's the particles in the background at 20% are index matched out, so you can't see them, but there's some level of tracer material that's left in, so you can see the streamlines. And then we track the tracers again. And so what we see is that the behavior doesn't look the same. And the Reynolds number is exactly the same. So the Reynolds number here was 200 based on the suspension viscosity. That is, we account for the influence of the particles on the viscosity. We go to Reynolds number of 200 for this case, and it looks quite different. However, there is still a recirculating zone in this region here. If one looks closely enough, you can find it. And so the bulk behavior is seen in the separation zone, but something else has happened out here such that it looks like a Reynolds number of 200 doesn't, I mean, what is a Reynolds number of 200 doesn't look like a fluid mechanical Reynolds number 200. So if we look at this at the trajectory, the following trajectories, a trajectory that could come down like this, one on each side we've tracked, then the fluid behavior would look like this. So they're slightly different because these are slightly different distances from the center line in both directions, but they're basically the same sort of trajectory. Well, we see the same thing for the particles, but instead of having the spiraling, it's killed. So we don't understand this fully, but it's certainly the case that it's killed. And so this is in the third direction, which is a little bit hard to mentally grasp at the moment. So I just wanted to point this out. And then I wanted to give the idea that the working hypothesis of what happens here is easiest to think about here, is that I have, well, it's maybe easier even to see in the lower concentration. So here we have particles which are coming toward this wall, they have significant inertia. Even at the particle scale, they have significant inertia. And so they reach closer to the wall than you would otherwise expect. And they're moving rapidly, more rapidly than you would expect for a Stokes flow. And so as a result, what's happening is that you're getting a strong squeeze flow in the fluid mechanics there, and that is then communicated to particles which come in behind them. And so that's creating very, very strong squeeze flows, which create large dissipation. So it appears that this region here is leading to very large dissipation when we go to higher concentrations. So in particular here, when we go to concentrations of 20%, this is creating sufficient dissipation that we no longer see that characteristic inertial behavior, even though at a bulk scale, the Reynolds number looks like it should be 200. This dissipation that's occurring here is much larger than one would expect just from a fluid mechanical motion, because we have all these close gaps between particles which are causing very intense dissipation. Okay, so that's as much as I feel that it's safe for me to say. So I'm going to stop. It's very close to 10:42, at which time it will be a hitchhiker hour. And just say that inertial suspensions have been studyable by various different simulation methods for a number of years now. And so Laz Boltzmann is what we use. The group of Martin Maxey and Eric Clement have developed force coupling method approaches. There's immersed boundary methods that are used, and including Eric Schockfe's group that we've worked with. These calculations are all demanding. They require careful numerics, but they're accessible. And when you think of expensive, it's just that you have to worry about how many particles you can do in a given flow. One of the points I wanted to try to make is that even single particle flows are complex, and the rheology is Newtonian at single particle level. We're not really accessing the full rheology. We're describing the stresses in simple shear flow. So we can't say that we understand the rheology very well, but we've characterized the stresses in simple shear flow. And then the last two flows that I showed of Taylor-Couette and the bifurcating channel, if anything, they show that the fluid mechanics of suspensions is really just a field in its infancy. And there's enormous amounts of work to be done to understand how to model and characterize these flows well. And that brings in the value of good experiments, good theory, simulations. So there's lots to be done in this area. So thank you all for being hitchhikers in this little effort to understand suspensions at different levels. So I'm glad to try and answer any other questions.
Thank you, Jeff.
Thank you, Jeff. Is there any question in the audience?
I can start with a short question,
Yeah.
and that's about the flow, so the wake behind in the back of the particle. So my bet was in particle 4, Lea 2.
Yeah.
I didn't think about the fact that there could have been a transition to the second like vortex on the other side. I don't. I mean, okay, great. If you can go back to the slide, but I don't think it's necessary. My question is simply, have you checked, like, is there a steady state of this flow? If you have a lot of particles around this cylinder, would you expect to have or not have particles in the wake?
Well,
Or it's just coming and going away?
So, okay, I can answer that in a quick way. If I had small enough particles, and then I could certainly get to the case where I had just, for example, one particle in each lobe, seems to be able to be it's not a steady state, but it would always be there, of course. It could live there forever, one in each lobe.
No, but I mean, like,
very weakly.
if you start with a
But if they're
group of
large
particles,
enough, then they would still interact.
but if you start with particles that are in front of the cylinder, like you've shown that if they're not in the wake at the beginning, then they just go away, then they do not enter the wake. But could they
That's right.
enter the wake because of interactions?
Yes.
Okay, and
I didn't show it, be, you can force particles into the wake, and then okay, so let me answer the question carefully. Particles can be pushed into the wake by interactions, hydrodynamic interactions outside, or they can be perturbed out of the wake by those same interactions. They can be perturbed out as well. And that's like what happened here. The moving to the limit cycle makes them then subject to perturbation because they're right near the edge. And that was what we thought was maybe a mechanism for cleaning up the wake. And it's a part of the answer, perhaps. But so at a high enough concentration, then you have this potential for exchange between the wake and the free stream just due to hydrodynamic interactions, basically. Yeah.
Okay. Thank you. Other questions?
Okay.
Yeah.
I've escaped.
Well, it's been very clear, at least for me. Lots of
Yes.
topics, lots of things to think about. That's for sure. And I'm always scared when I think about inertia in rheology. I don't know you, but it's a very scary topic. With this, yeah.
I wasn't scared enough when I started. That may have been my problem. I didn't realize how it's a field where one of the things that's troubling about it is that one can get numerical results that then you can verify are seen in experiments, but you can still not understand them. And so I find that deeply troubling. So I'm excited about this area of study, but a little bit disappointed in myself. So it's always a feeling that I should understand it better, but intuition comes slowly, let's say.
That's why I'm scared about it. But as you said, it's incredible because it's somehow easy to do experiments and simulations with these kind of systems. But again, like I in my head while you were talking, I had a lot of why is it
Why?
showing this?
And in the sense that as a person who studies fundamentals, answering why has always been my goal. And in this particular problem, I feel a little bit like I haven't fully gotten there yet. So anyway,
Well, your works are for sure helping the community get there at some point.
let's hope.
Thank you again, Jeff, for your 3 classes. This was the last one, and that was great. Thank you for availability, your kindness of being here for 3 classes in a row. And thank you people for being here. We now have a spring break. Oh, let me stop the recording first.